This is Calculus 12, Chapter 2.1. We're going to do the first part of limits. One use of limits is estimating tangent. Let's look at doing tangents with secants first. We have f of x is equal to x squared. And let's estimate the tangent at x equals 2. We can do this with a table of values. So we have a table of values of 1, 1.5, 2, 2.5, and 3. We can estimate tangent with rise over run, which is equal to f of xb minus f of xa over xb minus xa. So using 1 and 2, we have f of 2 minus f of 1 over 2 minus 1. This is 4 minus 1 over 2 minus 1, and that's just 3. Using values 2 and 3, we have f of 3 minus f of 2, 3 minus 2. That is 9 minus 4 over 3 minus 2, and that is just 5. So if we look here, we can see the first one as being this, and the second one being this. You would expect the actual slope of the tangent to be in between this value. But let's look at some more values first. F of 2 minus f of 1.5, 2 minus 1.5, and we have 4 minus 2.25 over 2 minus 1.5. That's 1.75 over 0.5, which gives us a value of 3.5. And the last one, I'm just going to skip ahead a little bit. This is 6.25 minus 4 over 2.5 minus 2. And we have 2.25 over 0.5. And we get 4.5. So the thing that we notice is that these values, which are closer to 2, produce slopes that are closer to the actual slope. We can assume that if we take even smaller intervals, we'll get closer to the real answer. So let's use limits. Limit h goes to 0, f of x plus h minus f of x over h. We are taking x equals 2. So you would have seen a value like f of 2 plus h minus f of 2. H is xb minus xa. Okay, so this would have been, if we had h as 0.5, we would have had 2.5 minus 2. So that's what it looks like with actual values. In calculus, we like to use a lot of things with just variables and no values. It's a little bit more abstract, but it gives us a little bit more power. So now we have limit h goes to 0, 2 plus h squared over h, and that's minus 2 squared. Remember, f of x is x squared. So we substitute the whole thing, 2 plus h into the squared. Now we have limit h goes to 0. We have to expand this, and we get h squared plus 4h plus 4 minus 4 over h. You haven't been taught limits yet, but the way to read this as h approaches 0. H does not actually equal 0 because we want the intervals to get as small as possible without actually being 0. If we substitute 0 in here, the answer is undefined. As long as we're not at 0 but close to 0, this will have a value. Okay, we can simplify a bit. We cancel those out. And now we have limit h approaches 0, h squared plus 4h over h. Now we can cancel some stuff out. Cancel the h, cancel the h, cancel 1h. And now we have limit h goes to 0 of h plus limit h goes to 0 of 4. And this is 0 plus 4 equals 4. So the actual slope of the tangent is 4. And looking at these values, it's right between all these values. We'll go over the limit properties later. I just want to show you what it looks like. There are other uses for limits. So here we have f of x equals x minus 1 all over x squared minus 1. We want to find the limit as x approaches 1 of f of x. I should write this down. We say limit as x approaches 1 of f of x. Let's note that f of 1 is undefined because if we put 1 in the denominator, we get 0. So let's evaluate this limit. Limit as x approaches 1 of x minus 1 over x squared minus 1. This is limit x approaches 1, x minus 1, and we factor the bottom. We get x minus 1 times x plus 1. When we don't see a way of simplifying it, we factor, and then we can use the limit properties. So this is limit x approaches 1, 1 over x plus 1, and this is 1 over limit x approaches 1 of x plus 1. And this is 1 over 1 plus 1, which is 1 over 2. Okay, looking at this graph of that function, f of x, we see that as we approach 1, we can see that the value is going to be a half. And if we approach from the right side, again, it's going to be a half. And basically, this is a function with a hole. Now, let's change this function. This is just f of x. We'll define g of x as a piecewise function of f of x when x does not equal 1. And we'll let this function equal 2.5 when x equals 1. So here we have 2.5 when x equals 1. This is g of x. This is a piecewise function. The question is, what is the limit as x approaches 1 of g of x? We have a value here. However, the limit is defined as what happens when we get close to the value, not what is at the value. So the limit is still 1/2. And again, not at the value. It's when it's close to the value. So here are some limit properties. If we have a constant value, the limit as x approaches c is just that constant value. Now this looks complicated, but it's actually fairly simple. If we look at a graph of x and we look at what happens at c, what happens when we get close to c? Well, this value is just c. Because as we approach from the left or right, we're going to approach c. This is the main limit property that you'll be using to solve most limits. So if we have L, M, C, and K are all reals, if we have a function where we know the limit is L as x approaches c, and we know that g of x equals m as x approaches c, it's important to note that these are both finite. They can't be infinite. We can use all these properties, the sum rule. So if we add f of x and g of x, we just add the limits, L plus m. Difference rule, f of x minus g of x, the limit as x approaches c, will just equal L minus m. And these should just be fairly common sense. You wouldn't expect multiplying two functions and adding the two limits. Constant multiplier. We just pull the k outside, and then we have limit f of x, which is L, and so we just have k times L. The one that's a little bit more difficult is the quotient rule. M cannot equal 0 because we're dividing by m. And another one that's used a lot, especially for polynomials, is the power rule. We just find the limit as x approaches c of f of x, and then just raise that to the power of r divided by s. And r divided by s are integers. Okay, we can't use these rules on a polynomial directly, but we can use it on each term. Here, you might recognize this function as x cubed. So we're doing the tangent of x cubed at 1. So this is limit h approaches 0. We expand this using the binomial expansion theorem. And that's h cubed plus 3h squared plus 3h plus 1. Minus 1 all over h. We cancel out the 1's. We can cancel out an h from each term. So we have limit h approaches 0, h squared plus 3h plus 3. Now we have the limit. We're using the sum limit law. H approaches 0 of h squared plus limit h approaches 0 of h plus limit h approaches 0 of 3. Sorry, this is 3h. So h squared as h approaches 0 is simply 0. And we can use the constant multiplier rule, pull that out, and we know limit of h as h approaches 0 is 0. And here we're using the constant rule. So this is 0 plus 0 plus 3, and that's just 3. We can use the power rule here, or we can just use the product rule. This is the limit of h times the limit of h. And both of them are h goes to 0. Another way of doing limits, especially for piecewise functions, is to do a left-hand limit and a right-hand limit. We write x approaches c from the left. This is a minus sign, that's a superscript. And we have limit x approaches c from the right, and this is a plus sign, that's a superscript. So let's look at this. In addition to solving algebraically, we can solve this graphically. We are looking at the limit as x approaches 2 from the left, x approaches 2 from the left, and we can see that it approaches 1. So 1. This is even though f of 2 equals 3. F of 2 equals 3 here. Remember that a closed dot means the value's at that point. An open dot means there's no value at that point. If we look at the limit as x approaches 2 from the right, f of x, this is equal to 3. Because as we approach 2 from the right, it approaches 3, and it doesn't matter that the value is there. It's approaching there regardless of what the value is at that point. For a two-sided limit, this symbol means if and only if. So if we have this is true, then this is true. If we have this side is true, this side is also true. That's what we mean by if and only if. If this side is not true, then again, this side is not true either. And as I mentioned, we usually do left and right limits when we have a piecewise function and we evaluate it at the boundary. Here's a piecewise function, the absolute value of x. It's defined as x when x is greater than or equal to 0. It's defined as negative x when x is less than 0. So let's do the limits. Limit as x approaches 0 from the left. Absolute value of x equals the limit x approaches 0 from the left, and we take the definition, minus x. And this equals 0. We pull out the negative sign, and we're taking the limit as x approaches 0 of x, and that equals 0. Limit x approaches 0 from the right, absolute value of x. This is from the positive side, so we know limit x approaches 0 from the right of x, and that equals 0. And if you don't remember, we'll graph this out. You can see that that is the absolute function. As we approach from the left, we see that it goes to 0. As it approaches from the right, we see that it goes to 0. You will need two more things to help you complete the homework exercises. One is the integer function. It's also called the greatest integer function or the floor function. So basically, it just removes the decimal part of a number. So you would see a closed dot and an open dot. So this is 1 and 1. So we see 0 all the way along until we hit 1, and we jump up to the next value. It's 1 all the way across until we hit 2, and we jump up to the next value. So that is the floor function. Another thing you need to know is this limit is a property. For now, you'll have to accept that sine x over x as x approaches 0 equals 1. This is solved with L'Hopital's rule, which you will learn later on. And that completes this lesson.